In this presentation from a recent international conference on Gerontechnology, Professor Tong Kai-yu from the Department of Biomedical Engineering at the Chinese University of Hong Kong discusses how the use of advanced technologies such as augmented reality systems assists in rehabilitation training. Professor Tong also shares his work on different exoskeleton robotic models, which help patients who suffer from strokes to exercise in their home independently, speeding up their recovery.
Today I would like to share about our works and also the development on the robotics and AR system. First of all, I'm a biomedical engineer, and but I come across with a stroke survivor, and you can see this lady. She smiled very happily. What makes her happy? After stroke, actually, she stay at home most of the time. But can we regain her functions to become independent? She can go around, So that is something in our mind we want to build in the robotic system. So you can see we build a robot, not just a simple robot. Actually, the robots can regain their independence, like climbing stairs. So later today, I will share with you how we are going to do that. Besides the robotics, actually, there's a lot of latest technology around us, like the wearable technology. I'm fortunate enough to be the editor for this book. So if you are interested in wearable technology, you can also read these books and then have more idea how technology can be used for the medicines and healthcare. So some of you may be interested to know what's biomedical engineering. Actually, it's very broad. It's how to integrate the engineering together for the medical applications. Myself is more on the medical instrumentation and biosensor, and also medical imaging and informatics. So today we'll look at the robotic system and the AR system. So let's look at what we have done. We are not just research. Actually, we move our research to the community. And recently we got funding from the Jockey Cup, and we built platforms to transfer our technology in our lab to the community, to the NGO center, to the to the stroke rehabilitation center. This is our website. Because of the COVID-19, a lot of clients, users, cannot come to the center in the second wave or the third wave. Then our lab, together with the 4 NGO, together, we actually build different YouTube. I think some of you may be doing yoga or other exercise, at home, during the COVID-19 period. How about for the stroke survivor? Actually, we have make 5 sets of exercise for hands, lower limb, so then they can do exercise at home. Besides that, actually, we also have technology for those more than 20 centers that we target to. You can see here we have the hand of hope for the left-hand side, and we also have ankle robots, and we also have a cycling system. And last is the AR system that we have built. If you want more information, actually, you can visit the website. It's called the Hope for Care. So let's look at what's the AR system. Actually, this is a new project we have initiated just a few last month. We have an AR system for the hospital and center, but we are thinking about in the COVID-19, can we move those technology for the home use? So we have launched this new initiative. So this is the first time I share to the public audience to see how it works. So let's have a look on this short video about the concept of AR home. You can also visit our website, AR Home. So the concept is we have therapists together with us, and they will set up the training module at home, what the client need to do. Then the system will detect the body skeletons using the Kinect sensor and with the depth sensor. Actually, we can see all the movement from all the segments. With those movements, then the system will automatically give you the score and the performance indicator. So the subjects will follow the correct movement from the video, and then also with the scoring. The data will be transferred back to the center. The center staff can look at it and give a phone call, and then to tell them what posture you can further improve. So this type of training can be do it every day, for maybe half an hour. So it's even in the COVID-19 period, this will be very, very useful. So what we need from the system is very, very simple. Every home just need to have a TV with the digital TV with the HDMI, and then we just connect with our computer. And one more thing is the Kinect depth sensor. That's it. Then they can do a training at home. And you can see there's a yellow dot, and that's to guide the subjects to do all the action. And then so they just follow it. All the training protocol will be set up by the therapist. And the beauty of it is the user get the real-time feedback. So the clinician don't need to the real time to work together with the client. The client just do the exercise at home. The therapy have time, can look back the data, anytime they want. Not just doing the exercise without tools. Actually, you can have this stretching band or even a yoga ball. So there's some of the tools can be integrated with the training to make it more therapeutic effect. So you can see there's a lot of special designed training activity. All this activity actually is developed by the OT and PT from the center. So they're using those techniques in the center. Now we can convert to the home training with the guidance of the AR system. At the end, you can see we have the report to the clients and also for the clinicians, so they know what's the range of motions, all the joint angle. At the end, you can see the small characters here. Actually, there's 3D models. You can move around this 3D model, in different angle, and you can see the performance. You can pay back the skeleton. So that's the AR system. It's very simple, user-friendly, and if you want more details, you can contact me. The other thing is about robotics. Okay, so it's besides software, we also build robots. So let's have a quick look what type of robots are around us. Before, there's a lot of big robots we call fixed and grounded robots. You can see in the hospital. They're very powerful. They can do a lot of big joints like the shoulder and lower limb. But nowadays with the technology, we can move it to become portable and mobile. So you can see on the left-hand side, we call it is an exoskeleton, and can be upper limb and lower limb, just like the Iron Man. On the right-hand side, actually you can see not just the robot can move. Actually, we can follow the intentions of the user. So we can use the muscle signal, like the figure D, and also the figure H, use the brain wave. And both will detect intentions and drive the robot to move according to the user intention. That will be very useful for the rehabilitations. Robots have been developed very, very quickly. From the big robots, you can see from the left-hand side, nearly 20 years ago, and then just a single arm. And then later on, 2 arms, and then become exoskeletons, single size and dual size. So it becomes a lot of applications. So this is increased the applicability of the system for the rehabilitations. So this is from one of the lab, and then you can see that the robot is from 1 degree of freedom to multiple degree of freedoms, and then later on you can see that they can also integrate with the VR system. The technology evolves so quickly. You can see that all the robot is really like the Iron Man, with all these metals, aluminum, irons, to build all these robots with the motors. But recently, there's a technology we call the soft robotics. So we can make some of the polymers, silicons to make the soft actuator. That will make it more lightweight and also create a lot of interesting functions. You can see this is the table of the publications of those research. You can see the recent year, they've increased rapidly. The red one is actually for the journal that we have robotic system, and then the blue one in the lower figures is actually a soft robotic. In our lab, we have both systems, and I will share the technology behind. Hopefully, you learn better what's the pros and cons of the system. In Hong Kong, I think stroke is the leading cause of disability, and also for the world. All of us know this. For the stroke patients, the first few months is the important golden period. If they can recover better, long term will be much independent than the others. But in Hong Kong, the length of stay after stroke is less than a month in the hospital. So then how about the other 2 months? Actually, you maybe have some of the outpatient service, but you cannot do it every day. So what's the best way to do it? If we can do some of the home-based training, or the others outpatient center can do the training, that would be good. So the market is huge. You can see in China, in Hong Kong, there's a lot of patients need those services. For the robots, we follow the physiotherapists and occupational therapists. So what type of actions normally they will recommend the user to do, and then we'll build the robot to suit the purpose. So you can see this is one of the designs for the shoulder, elbow, and wrist. And some of them even with a backpack, to control the elbow flexion extensions, and they call this exosuit. So they have a different name. Exoskeletons, exosuits. Those is the names in our field. How to control it? As I mentioned, in the past, a lot of robots, they use this force feedback to control it. But nowadays, they find it even better if you can use this muscle signal, electromyogram, EMG, or the electroencephalogram, the brainwave, to control it. So let's look at what we have done in Hong Kong. Actually, I start with this robotic rehabilitation since 2006. At that time, we have the German gate trainer system. Quickly, in 2008, we developed our first robotic tower we called poly-J-bot. With the technology advance, actually, we can make it smaller and more functional, and we built a hand hook in 2011. Later on, we built an ankle robot, knee robot, soft robot, and the shoulder robot. So there's a lot of robots ongoing. And then today, it's my pleasure to show you some of them. So let's look at the big tower. At that time, we think about if we can integrate the robots together with the human intentions, maybe have a better recovery. At that time, we want to collaborate with other centers and also other manufacturers in the world. But at the same time, the overseas manufacturers, they're not interested for research collaborations at that time. So what's happening? There's no options. We need to build our own. Then we can implement the algorithm for control. Then we build this robot. Then we can integrate this EMG control. So how it works? Actually, very straightforward. If the patient wants to extend the elbow, but they don't have enough power because of the muscle weakness and also the spasticity, so they cannot fully extend the elbow. Then what we can do, the motor underneath can generate the power. But how to control it? If we can detect the muscle power is much stronger from the tricep, for example, for the elbow extensions, then the motor will generate the power for them. If the patient relaxes, the motor will not move. So actually, larger the intention from the subjects, larger the EMG, the motor will generate a much higher power. And the system will be calibrated for each individual. So the individual can generate maybe 10 Nm, then the robot will match maximum 10 Nm. So it will match with their own ability. With this type of training, the subjects just need to do is I just exert the power. Maybe I can exert 5 Nm, then the robot will generate another 5 Nm for me. Then I can have enough force to extend my elbow. And then I will follow some of the target and do the training. So this is what we try. The logic behind is if the brain notice the signal is correct, I can generate the power. So we reward the brain. You can complete the functional movement. So through this training, and we find out is that the results very, very good. The brain actually we learn. This is what we call the neuroplasticity in the brain. We conduct a very interesting study. We compare two groups. One group just passively using the robot to move the wrist joint, to do this flexion extensions. The other group is using the EMG, to control the wrist robots. So using the extensor digitorum and flexor digitorum to control the movement. The interesting result is using the muscle signal to control the robot, the recovery is much better. So we can see the wrist, elbow improve very well, the spasticity have been reduced, and the functions after 20 sessions is remarkable. We stop the training, we ask the subjects to come back 3 months later, the function still can maintain. So it's very good. We can see the improvement. What's happened to the passive training? We just can see the spasticity have been reduced in this wrist flexor. The other things didn't improve. The worst is after 3 months, the spasticity come back. So the brain doesn't learn anything. So what's the story tell us is if we have the robot itself, it won't work. The robot must include the human intentions. Then the system will generate brain motor relearning for the patients. So this is a very important lesson we learn about it. And the other important lessons that we learned is when we do the wrist robot training, we can see the improvement in the wrist and elbow. And, but we also have another study. We do the training just on the elbow, the effect just in the elbow joint, not on the wrist. So what's happening is it seems if we can train the distal, like the hand or the wrist, then you benefit not just those regions, they benefit the whole upper limb. That would be good. So we don't need to do the training one by one. We can start directly from the hand and wrist. Because of that, we start to think about, can we build a hand robot? When we look at the hand robot, at that time, it's nearly 10 years ago, not much research, and most of them is very big, bulky, and some even just a single fingers movement. So we think about, can we build something interesting, At that time, I don't think the movie of Iron Man is launched, So we are before the Iron Man launch, at that time. So we think about, can we build something beyond what's available in the technology? One thing is, can they use their own hand to manipulate with some objects? So we think about, how about exoskeleton hand? So this is what we built. Hand is the most difficult part after stroke to regain the functions. So it's not a lot of researchers want to spend time to do that, but we think about, if we get the intentions, we get the exoskeleton, maybe it works. So this is how we start the journey. So our robot is very portable. It weighs less than 1 kilogram. It's built by aluminum and 5 linear actuators to generate the power. We didn't use the conventional method, using the cable to drive with motor. That will make the system very bulky. We also generate the mechanical structure, so one motor can generate 2 joint movement, so we save a lot of space and power. The function is the same. At the end, definitely we need to use the EMG, the muscle signal, to drive the system to do the hand open and close. After that, good news is it works. And thanks for the support from the Jockey Club. Actually, many centers in Hong Kong already have the benefits to using the hand of hope. And also we are working to modify the system, enhancing the system, so making the system even better and better, even today. Fortunately, we also licensed the technology to a company, so now the technology can sell to 15 countries as a medical device. So this is how it looks like. We also have an open hand design, so the subject actually can feel the objects when they manipulate the hand with the robot hand. So I showed you how the system work with stroke patients. So this young lady used the affected hands to grab the spongy. You can see she barely can grab it, but she cannot release by herself. So with the robot hand, so if you listen carefully, you know, what she just said is, wow, she said I'm moving it by myself. That's what she said. It's actually, she didn't think about I can move my hand by my intentions. And, but actually, this is what we are trying to do. So we use these ones to do the training for all the patients. So let's to have a quick look, you know, after training, without the robot hand, does it regain the function? So we have a couple of videos to show you how the system benefit to the patients. So you can see the lower one is the affected hand from the stroke patients. We want the subjects to do the lateral pinch, but she have difficulty to control the thumb positions. After 20 sessions of the training for half an hour, then you can see she can do it by herself without the robot. Then there's a lot of small object edges you can manipulate with her bare hand. How about 3 months later, without the robot hand training? She still can do that. So she can use the hand for a long period of time, you know, to do all the tasks. So if we can move the technology earlier, you know, in the hospital, then is it better? Actually, yes. So you can see this is the patients with a stroke just 4 weeks. Left sides have been affected. After 10 sessions of training, much better. And how about after 20 sessions? Wow, look marvelous, okay? So we have around 70% of the stroke survivors have the remarkable recovery. So it's very, very good. Actually, that also make other research groups and research labs start to work on the hand robotic system. From the results, we can see from the clinical score, like the Fugl-Meyer for upper limb and the ARAT and Wolf test, and all show the improvement in the clinical score. Particularly for the ARAT score, actually it's there for the hand functions. And for the elbow robot, wrist robot, we couldn't see any improvement. But for the hand robot, first time we see the remarkable improvement. And also the spasticity have been reduced for all the joints. So it's really good for the stroke survivor. So more details you can refer to our publications. So how about using a brainwave? Yes, our lab also working on the brainwave, and then we find the results are very similar to using the EMT to drive it. This is our research assistant, so he is not a stroke patient, but actually we can use the brainwave to control left hand or right hand with the brainwave. So we also analyze the brainwave with the electroencephalogram, and then each patient had different pattern. But nowadays with the technology, we can identify their own pattern to drive the robot hand. Upper limb, we have this big tower and also the hand of hope, very practical and useful. Then how about the lower limb? Lower limb nowadays, you can see it in overseas. They have this exoskeleton for walking. They move from the left-hand side. The big tower, you can see some hospitals still using it, and then move to the exoskeletons. Both systems actually cost more than $1 million Hong Kong dollar. So it's very expensive, And the other thing is one hospital cannot equip with many set of this system. Then the number of patients can benefit from using those systems is limited. So we think about, can we benefit more patients to make a more cheaper versions, more affordable versions, and more important is make it portable rather than those bulky design. Why they need to do this? Because they originally designed this system is for the spinal cord injury, so it's a bilateral have been affected. But for stroke patients, actually it's unilateral for most of the case, so we don't need the motor for both sides. We just need for one side only is enough. Back then, 20 years ago, we also conduct the interesting study with the Dongwa Hospital Physiotherapy Department with Dr. Lenoni. We have an interesting randomized control trial to think about if we can, this big robotic system to do the loading training in the earlier stroke, it said recover much better. After 20 sessions of training in hospital, and then 6 months later, are they still can maintain a really good function? This is the question. At that time, there's no study in the world can do that, but Hong Kong is a small place. It's very convenient, and also, with the support from the hospital, we can do this earlier trial. So we are the first group. We conduct this trial at that time. So we separate the group into 3 groups. One is the control group, we call the CT. The other is a gauge trainer using a robot. The last group, we also add the electrical stimulation to see whether the stimulated muscle will improve the functions. So we have 3 groups and see the result. The results are very good. After training, and then also we look at the 6-month follow-up. And from the first 6-month follow-up, conventional training in the hospital, they can walk independently. It's around 42%. So they can walk with a crutch or by themselves, in the community, in the level ground walking. We use the FAC level 4 as the cutoff. When we look at the gauge trainer, system, they can increase them to the 64% walk independent. When we look at it with the stimulations together, we can further improve it to the 81%. We are not the only groups can see this result. Few years later, the other group also repeat some of our experiments over the world. Then there's a meta-analysis conduct. They find out at the end, the conclusion is, if you can do the lower limb training within 3 months, the effect will be significant. If you have the training beyond 3 months, maybe not very effective. So this is a very important message. And so those mechanical training actually can improve the independent walker. So actually we are the first group to demonstrate. Later on, the other research group also demonstrates the same result. So nowadays, it's a very good hospital will try to do more long training at the earlier phase. But the problem is, they just stay in the hospital for 1 month or 1.5. How about another 1.5? So if there's some system, they can do it more frequently with the walking, the result will be better. So we think about, can we make a small design? The material we change to the carbon fiber we can build, and also we have some of the mechanical designs. Actually, we can empower the small motor, with a bigger torque, and then we can reduce the weight. The last thing is we have some of the sensor, so we can detect the walking patterns, automatically. So when they want to walk faster and slowly, everything is automatic. And then we also target to walk upstairs and downstairs. So the total weight is around 500 to 800 grams, much lighter. And so this is our design. So the sensor inside is actually, we have the motion sensor, force sensor to determine the walking intentions. Now our designs can work for overground walking, upstairs, downstairs, and even we build the knee and hip robots. But most stroke survivors, they suffer from drop foot. So the ankle robot is the most popular one. So this just gives you a closer look about the robotic system. You can see we have this gear transmission system to transmit the power to the ankle joint. We also have a sensor inside embedded in this carbon fiber to detect the force and the motions. So this is the video you can see. The subject's now not fixed with a big tower of robotics. He can walk around and even go upstairs and downstairs. So the space is not limited. And definitely the mobility will help the clinicians to do the training, even any stair, in the hospital. So I showed you one more video about this system. You can see here is the first day. I think day 4 for these subjects to walk without the robot. You can see it's, the walking not very good, and but after 13 days of training with the robot, if you are a physiotherapist, you notice this is remarkable, and then that's really good. This is what we do. So our training is still ongoing, and the recent result also show that chronic stroke patients, it means a stroke more than 6 months, we also can see the improvement. So that's really good. In the past, we couldn't see that, but now it seems more walking will be better for all the patients, even they have a chronic stroke. So the study is still ongoing in our lab. Recently, from last year, we also collaborate with the HA. We think about how about some of the patients with the polio, because they have some cases come to us. Nowadays, I think polio is gone. We don't have new cases. But back then, 50 years ago, we have suffered a lot of polio patients, and they still survive nowadays. So what's happening is, in the past, they still can have this orthosis for them to walk around. But because of the age, reduce the muscle power, so they cannot walk with the orthosis. They may become wheelchair bound. Before they can walk around, now wheelchair bound, that's not good for them. So think about, can we build a robots to empower them so they can still continue to walk maybe for another 10 years. So this is the designs. And you can see that we have this lock mechanisms and then also a motor. So we can lock during the stand phase to maintain the body weight support, and then the motor will help to flex the knee and generate the movement. And we have the sensor inside, so everything will be automatically triggered on and off. So this is the cartoon to show you when the system will be locked during the stand phase, and then when it's unlocked during the swing phase. During the unlock phase, then the motor will take part and then generate the movement. So this is the whole setup. It's very portable and simple to use. And then you can see the sensors in the insole, and then to trigger the system. This is what the subjects need to wear. The weight of the system is also around 1.5 kilogram. It's similar to the system they use for the KFO. Then we have 3 subjects trying the system, and then we want to see the result. Before and after the training with the device, left-hand side is the conventional brace, and then you can see the subject need to lean forward to maintain the balance, because normally it's lock the knee. But now with the motors, they can unlock the knee, and then also with the support during the stand phase, actually they can walk with more upright positions. That's good for him. If you look at from the back, actually you can see because the knee have been locked, actually they need to swing the trunk during the swing phase. And then you can see the swing angle is much larger than us. But now the knee can bend, actually they can generate a more balanced walking patterns. They don't need to swing the trunk compared to the past. Last topic I would like to share with you is the soft robotic system. So because the material have been improved nowadays, and then we can not just use metal, we can use the silicon and others. On the left-hand side, they still using some of the numeric, using air to pump the actuator. So the things are similar to our linear actuator for the robot hand. Some may be using the artificial muscles to pump the air and then to shorten the actuator. But recent developments is actually using the air directly interact with the soft robotic system. That will be more direct, and then the efficiency will be higher. So actually, we are developing the C&D in our lab. But one of the interesting targets is we have some subject is a very young age, just maybe 7 years old or 10 years old. A kid also can have a chance to have a stroke. And then we are helping those kids to do the training in our lab right now, because we are building this 3D print soft robot hand. Actually, we can print a very, very small size robot hand for them. So that will be benefit to those pediatric cases. So I think it's a very, very meaningful work that we are doing right now. So I showed you my last video to all of you to see our development in our lab, how the actuator move, and then what things we are working on, and then see some of the patients, how they regain the hand function. Because these robots maybe help them to do some of the very, very fine movement, because of the soft material. So and then the function may be better for some cases. So we just pump the air, release the air, the finger will bounce back. So the subject can grab the pens with the soft actuator. So there's a lot of objects they can try to grab. A wooden box, a ball. We are doing those training in our lab right now. So this is the video before the robot hand training. So we have a very difficult task. Grabbing a coin. I think it's very difficult for most of the stroke survivors. But after 20 sessions of training, same subject, wow, they can do that. Okay. So if you are a physiotherapist or occupational therapist, you notice this is not easy task, and then she just managed to relearn it. So this subject, we want the subjects to do the more individual finger movement, but she have difficult to control each of them. But after training, and then she can also make this V-shaped, the hand posture. So hopefully we can have more stroke survivors can benefit from our technology. So that's all for today. And the take-home message is I hope all of you learn more about the human body conditions, the brain, the muscles, how we gain the functions, and then also the latest technology, the AR or the robotic system. And together, I think we can have better solutions, better technology for the medical, fitness, and lifestyle. Hopefully, our technologies can bring better health to all the human mankind. So thank you for your attention. Thank you.